All right, guys, welcome back. And today we're going to be going over 6.2, which is linear and angular velocity. And for the think slash warm up, I say imagine you're on a carousel of death that spins insanely fast. Would it feel faster if you were near the center of the carousel or near the edge, right? And I think most of us would agree if we could imagine ourselves on a carousel that's spinning super fast, the edge would feel faster, right? Because we're moving um, more distance in the same amount of time that the whole thing is turning. And we'll get a little into about that with linear and angular velocity. But the first thing we have to go over is angular displacement, and that's just how far you've rotated on a circle, how many degrees, or we're going to be working with radians, right? How many radians have you moved? And so, if we start in standard position and then we go out here, we've moved that many radians, right? Theta radians. And we're going to include, like, if we go around like 5 times, then we're going to consider that like the whole 5 times, right? We're going to consider that 10 pi radians. So for our first example, it says determine the angular placement in radians of 4-point revolutions. So we have 4-point revolutions, and then we know that there's 2 pi radians per revolution, right? And if I were to write it like this, right, 2 pi radians per 1 revolution, we kind of see that the revolutions cancel, right? And that's called dimensional analysis when you use like inches and feet and things like that, and like units cancel each other out. That's dimensional analysis. And so we end up getting 9 pi, and it says round to the nearest tenth. So it's going to want 9 pi calculated out. So I'm just going to do 9 times pi in my calculator, and I'm going to get that is about 28, and then it wants it to the nearest tenth, so 28.3, and that'll be radians. We're in radians. So next, we have angular velocity. And angular velocity is the ratio of the change of the central angle to the time required for the change. And what that's really saying is just how fast is that angle changing, right? And so we have this little weird W here, right? Or let me draw a circle first. So, right, if we move from here to here, right, and we have this angle theta, it's saying how fast is that angle? Did we move that angle pretty much, right? So we have angular velocity is given by the equation. This little W is called omega. It's a Greek letter. Omega equals theta, which is in radians over time. And then I just said down here omega is the angular velocity. Theta is the angular displacement, which should be in radians. And then T is in time, whatever it should be, seconds, minutes, hours, you name it. So, and then down here I have, does the angular velocity change the farther you are out on that death carousel, right? And so the answer is no, right? Because whether you're on the inside of the circle, so let's say this is the death carousel, right? Let's say you're right here in the center, right? You go around just as fast as someone that's out here, right? This person goes 180 degrees just as fast as this person goes 180 degrees. So the angular velocity is the same no matter where you're at, right? And that makes sense because in our equation, we don't have anything about distance out, right? It's all just about the angle and the time. So determine the angular velocity of 7.3 revolutions are completed in 5 seconds. And so we have omega equals, we have 7 point, well, first of all, we need theta in radians, right? So to get that, we need to do 7.3 revolutions times 2 pi radians, right? And if you just want to times it by 2 pi, because every revolution is 2 pi and that makes sense to you, that's totally fine. I'm just doing this because we're going to need it a little later on in this section to get used to it. So 2 pi radians per 1 revolution. Revolutions cancel. And so we have theta equals 7.3 times 2 pi radians, right? And so that's going to be 45.867 radians. So that's how many radians we've moved. And then omega, the angular velocity, is theta divided by time. Well, it just told us that omega equals, and then we just found that theta to be 45.867 radians. And then it told us up here we completed that in 5 seconds. And so when we divide that thing by 5, we get that omega is about, I don't know if it told us to round it all, then 9.173. And now we're in radians per second, right? Which also, those units make sense, right? Because think of just a normal velocity, speed, right? Speed is usually in feet per second, miles per hour, right? Unit of distance per unit of time. And angular velocity is kind of the same thing. It's unit of angle, right? Radians per time. So that makes a lot of sense in my head. So moving on, I'm saying you and a friend are on the carousel of death from earlier. The carousel makes 13 revolutions per second. Your friend is on the inner circle of animals about 9 feet away, and you are on the outer circle, which is about 35 feet away from the center. Determine the angular velocity for you and your friend in radians per minute. So notice that we're giving it in revolutions per second, but then we get radians per minute. So we're going to have to change per second to per minute. But keep in mind, we just said that it doesn't matter how far away you are out of the circle for angular velocity. So at 9 feet away and 35 feet away, stuff is useless. We have omega equals, so we have 13 revolutions per 1 second, right? And we're going to need that in 2 pi radians per 1 revolution, right? So that's just what we've done before. The revolutions cancel. And now we already have our per second, but now we need it per minute. And so we're going to go, 1 second up top. Or I think it makes more sense to say there's 60 seconds in 1 minute, right? Because then these seconds are going to cancel out, and all we're going to be left with is radians per minute, which is what it wants. And so that's the dimensional analysis that I said we were going to need. So we're going to need to do 13 times 2 pi times 60. And we get 4,900.88 radians per minute. And that's a lot of radians per minute to go, right? And that's why it is a carousel of death. That is going to wrap it up for the first part of 6.1. The second part, we'll get into linear velocity.